Okay, so thank you very much. So let me first say that I'm very sorry that I cannot be there. The travels are open again for people going to Europe from the US, and now even for people from Europe coming to the US. But I have a kind of complicated visa situation at the moment, so traveling outside of the country is actually not easy for me. Okay, so as I stated in the title of the lectures, the objective of these two lectures, of the one of today and the one of tomorrow, is to go through the convex integration approach for the Sagar conjecture, tell you a bit on how the conjecture was finally proved by Phil Izet, and explore also some new problems which are like interesting and open, and which at the moment we don't know actually how to solve. So the object of study is the Euler equations, which I am going to write over here in the following form. So the first one is the momentum equation, and the second one is the conservation of mass equation. So we have a divergence-free vector field U, and it satisfies the first equation, in which the pressure P is actually a scalar. So the unknowns U in this talk are always going to be periodic functions on the three-dimensional torus, and defined on a time interval. So U is the function which gives you the velocity of an incompressible ideal fluid at the point x at time t, and P is a scalar, and it is the hydrodynamic pressure. Okay, and this quantity over here, if you were so this nonlinearity over here, if you were a smooth solution, this would be exactly equal to U dot grad U, so to the effective derivative of U along the flow. And in component, this is just, so if I were like to identify the I component of this vector field, this would just be the following one. Okay, and if you have a smooth solution, a very important identity is the conservation of energy. Which mathematically you can recover by scalar multiplying the first equation over here. Let me actually change to that. So by multiplying the first equation over here scalarly by U, and after elementary calculus manipulation, you actually end up with the following conservation law. Okay, and upon integrating this in space, you actually come up with the conservation of what is physically the total kinetic energy of the fluid. Okay, so this one is the local energy identity, and this one is the global energy identity. Okay, so on the other hand, what we are going to consider in this case are solutions which are only weak, which are not regular enough to carry on actually these computations. And in particular, we are going to consider distributional solutions, for which the only thing that I need to make sense of is actually to be able to define this product over here. Okay, and you recognize immediately that as soon as I have a square summable solution, I can actually multiply the components of U, and I can make sense of this matrix as a matrix of L1 functions. And then I can take the divergence in the sense of distribution, and in all the other occurrences of the unknowns, actually the equation is linear, and solutions in the sense of distributions are well defined. Okay, so in this talk, we consider distributional solutions. Which are in fact continuous. And so if you don't like the usual definition of distributional solutions, what actually happens in the case in which you have continuous solutions is that from the point of continuum physics, they satisfy conservation of mass. In the sense that the flow of fluid across the boundary of any fluid element is equal to 0. And they satisfy conservation of momentum in the sense that if you take the time derivative of the momentum on any fluid element, this is equal to the amount of fluid or the fluid or like, you know, the amount of momentum which is carried. So the rate of change of the momentum is equal to the amount of momentum which is kind of escaping the boundary of your fluid element, omega, and the force which is actually exerted by the outside pressure. Okay, so these two identities for continuous distributional solutions hold for every fluid element omega which is sufficiently smooth. For instance, omega Lipschitz. Okay, so you could think about a sort of irregular fluid, which is anyway satisfying the conservation law of mass and conservation law of momentum in the sense of continuum physics. Okay, and there's a famous conjecture of Lasson Sagar, which is motivated by the theory of a hydrodynamics turbulence, which says that if U is actually a Hölder solution, C alpha, then if alpha is bigger than 1/3, the global energy identity holds. So the kinetic energy is conserved. And if alpha is less than 1/3, then actually there are solutions which do not conserve the total kinetic energy. And in fact, actually, if you look at Sagar's statement, what is really believing that it should exist is that there are solutions which should dissipate the kinetic energy. Okay, and this is
Camillo, could I ask a clarification?
Yes.
So when you formulated this continuous solution definition, I'm
Yes.
guessing there's no natural Lagrangian form of that because the velocity field is only continuous.
Correct. I mean, if you want to follow the particle trajectories, actually you have solutions by Peano's theorem, but you don't have a well-defined notion of flow that you could actually follow. Yes, that's correct.
So there's no natural way to formulate this in those terms.
Well, okay, so there are, of course, ways of actually formulating the Euler equations in a Lagrangian way and with some weak formulations, like as it is done, for instance, by Brenier and other people. It is not so clear how to link it to the Eulerian formulation, though.
It's very interesting. This formulation with transport of momentum is kind of neat because you don't have to worry about uniqueness of particle paths.
Yeah.
Thanks.
Okay, so this is actually a theorem. So the Sagar conjecture now could be actually called a theorem. So first of all, part one. Okay, so let me maybe write it over here. So Part one was proved by Konstantin A. and Titi. In the 90s, I think actually this was like 1994. And part two has been proved by Phil Isett in 2017. And in fact, with dissipation, Phil's proof has been improved by Tristan Buckmaster, myself, Laszlo Zekai-Hidi, and Vlad Nikol. Okay, so why actually Sagar was interested on this, and I mean, what is one of the possible motivations for studying these strange solutions is that they are in a sense a shadow. So these solutions might be a shadow of the so-called anomalous dissipation in the theory of fully developed turbulence, which postulates, so this is a postulate of the classical theorem of Kolmogorov, that if you have a solution of Navier-Stokes, if you have a typical solution of Navier-Stokes, in which your dissipation is, however, very small, and if you have a smooth solution, the global kinetic, the global energy identity actually becomes the following law. But with an epsilon in front, of course. And when you actually let epsilon go to zero, typically in a turbulent regime, what should actually happen is that this quantity over here, so the dissipation rate, is in fact sort of independent of epsilon under certain suitable assumptions. And of course, if this happens, you might wonder, if I take a sequence of solutions to the Navier-Stokes equations, which are actually smooth, but I let the viscosity go to zero, if I have a uniform bound on the rate of dissipation, in the limit, I'm either not converging to something, or if I am converging to something, in particular, if I am converging to a solution of the Euler equation, this solution of the Euler equation should be dissipative. Okay, and now, if you believe that the Euler equations are a shadow of or dissipative solutions of the Euler equations are a shadow of this phenomenon, of course, you might also remark that solutions of the Navier-Stokes equations, as long as they are smooth, they satisfy a corresponding local kinetic energy identity, which is given by the following equation. Right, and if that happens, actually now when you send epsilon to zero, this term, it's easy to see that it has to converge distributionally to zero, because you have a uniform bound on the L1 norm of modulus of u squared, but this term over here is what actually should be responsible for the dissipative part, so for the fact that dissipation is actually surviving in the Euler equations. And so you'd better study actually solutions which satisfy not only the global kinetic energy inequality, but also a local form. Okay, so this is what I'm going to call actually the local energy inequality. Okay, and you could advance then the following conjecture, which is a sort of strong form of the Sagar conjecture. And this would be that if U is a C alpha solution of Euler with alpha above 1/3, then the identity, so the equality actually holds in this identity. And incidentally, this can in fact be showed with the same proof that Konstantin A and TT use for proving the conservation of the global kinetic energy. So this part is not a conjecture. Okay, but the part which is actually still open is that for every alpha less than 1/3, that exists a solution U in C alpha for which the inequality is actually strict.
Camillo?
Yes?
Yeah, just to comment that this result, even though it follows from the idea of Konstantin and myself, it has been proven by Duchamp and Robert, just to give them the right credit.
Right, yes, that's actually true, sorry. In fact, I should have mentioned this before. It's in fact Duchamp and Robert who come up with this definition. Thank you very much. I should have mentioned that. So this is actually, so the first time that it actually appears in the literature, this definition of solution of the Euler equations which are locally dissipative is actually due to Duchamp and Robert. And as Edris was correctly pointing out, even though it follows from the same ideas which he, Konstantin and A actually used to prove the positive part of the Sagar conjecture, this fact here is also remarked by Duchamp and Robert. Okay, so coming back actually to the flexibility part of the Sagar conjecture, what then you would expect is that for every alpha less than 1/3, there exists a solution U in C alpha for which the inequality in the local energy inequality is actually strict. Okay, so and where do we stand actually over here? So let me just give you, so this problem is still open, but let me just give you a review of what is known in the literature. So first of all, a first construction of a solution which actually dissipates locally the kinetic energy. So just a distributional solution for which the inequality is strict is in a paper by Laszlo and myself. I think back in 2008. And this is just for bounded solution. Okay, then it's a work by Phil, who first constructed recently. I'm not sure, this maybe was like 2018, 2019, I'm not completely sure. So anyway, he constructed the first example of continuous solutions. Which can be upgraded to Hölder and subgraded in the same paper. And I mean, as it often happens actually in this type of constructions, as I will explain in the remaining part of my lectures, one thing that you can almost immediately see from the technology that we have in the literature is that as soon as you can actually break the continuous barrier, there is a certain Euler exponent that you can reach. And in fact, the situation is also not that bad, meaning that even the first Euler exponent that you reach by these constructions is not something ridiculous. It's still something which has more or less the order of magnitude of the conjectural threshold. And in fact, I believe Phil is actually getting like up to 1/13 minus. So every constant less than 1/13. And what seems to be the best that we can currently do, and this is a paper by myself and Hyunju Kwon from last year, I think we can get up to like 1/7, if I'm not mistaken. I mean, anyway, it's still a technical exponent. It's better than the exponent of Phil because we are able to implement certain ideas, but it's still pretty far actually from the conjectural threshold. Okay, so, and the aim of this lecture is now to give you an idea. So first of all, is to give you an idea on how you actually come up with an algorithm, or how you can come up with an approach to actually generate continuous solutions which kind of behave badly for these systems of PDEs. So, and this actually reviews the starting of idea of Laszlo and myself in 2012, in which we were trying to come up with a construction which is continuous a few years after we actually knew pretty well that certain type of technology for which you saw actually a glimpse in the paper in the talk by Jan-Kana Ryland before my lecture. Certain type of technology is actually extremely efficient to produce L infinity or discontinuous solutions to similar problems, and in particular it can be applied to the other equations which kind of behave in a strange way. So first of all, the aim of the lecture is to examine the philosophy behind what I will call C0 iterations for the Euler equations. Okay, and the ambition actually of this part of the lecture is to show you that there's a method that you can abstract from our works, which in principle enables you to try and check in several other situations whether your system of PDEs is amenable to a similar construction. So it goes beyond just like solving this particular question. There's actually something which one can extract as a general toolbox for similar problems. So the aim is actually to provide a general toolbox. Now, let me warn you though here, it's really a toolbox, like when you're trying, for instance, to solve some, when you're trying to make some minor repair in the house. So you've got the toolbox, which means that in principle, it's better than just being with your bare hands. But I'm not going to tell you that there's a method to understand right away whether you can actually solve the problem or not. I mean, you've got the toolbox. Well, then you open the toolbox, you look at the tools that you have, and you see whether the problem that you want to fix is actually can actually be fixed with the toolbox that I've provided you. And there's no guarantee that this is going to work. In other words, it's not really a very well-defined theory in which I can give you a nice theorem which says if your PDE satisfies the assumptions A, B, C, D, and E, then there is actually a convex integration construction which works in a certain regularity threshold. But there's a toolbox though. So this is the first thing that we will do. Then I will explain you what you actually have to overcome and what Phil overcame to actually get to the Sagar conjecture. From the flexibility point of view. And then finally, I actually want to illustrate you what happens when you get to the local energy inequality and why we're stuck. Okay, very well. So as it was actually already said by Marshall, plagiarism is a major drive in human enterprise. And let me tell you that part one is essentially stolen by a beautiful set of lectures, which has been given by Laszlo here at the Institute for Advanced Study, and which unfortunately are not recorded on the usual YouTube section of the Institute. So you will also not be able actually to see that I'm plagiarizing his lecture. But at least I think I'm doing something good, because these lectures, on the other hand, are recorded, and Laszlo actually made really an awesome job in explaining certain things. Okay, so let me start with the, kind of grandfather of these iteration mechanisms, which actually is the Nash scheme for isometric embeddings. And I will illustrate this, the basic idea of the scheme, and then we will just study how you can actually modify it, or how you can actually take certain ideas of Nash and kind of generalize them to a much broader context. Okay, so here is the model problem of the famous on the existence of C1 isometric embeddings. So let me just maybe be super clear over here. We are looking actually at the first paper, which was proving that as long as there are no topological obstructions, any Riemannian manifold can be isometrically embedded with a C1 map into the Euclidean space in codimension 2, which was later upgraded by Kuiper to the optimal codimension 1. Okay, so here's the problem then. So I have sigma G, which is a Riemannian manifold. And okay, for the purpose of this talk, what you can actually think is that sigma is in fact a patch omega of an m-dimensional ambient space, and G is a smooth metric. So which means actually that G is just a symmetric m times m matrix field, which is positive definite. Okay, and these coefficients Gij, which gives you, the entry of the symmetric matrix, vary as I vary the point x in omega. Okay, and what do I want to reach? So I want to reach actually an isometric embedding. So in the language of differential geometry, this would mean that I want a map U from omega, and I will actually be going into Rm plus 2, but I don't want to focus too much actually on this exponent over here. Maybe I want to even replace it with a sort of much higher codimension. So I want actually maybe to replace it with a much larger number. And getting down from this number to 2 and then to 1 is more like a technical refinement. And and this map U is just C1, and it pulls back the classical Euclidean metric on the Euclidean space to your metric G. So if I denote the Euclidean metric by E, this actually gives you the metric G, which in coordinates just means that when I take the derivative of U, transpose it, and multiply it by U, I actually get the matrix G. Okay, so this is also equivalent just to say that if I take the scalar product of the DI partial derivative and the DJ partial derivative of U, I actually get the coefficient Gij. Okay, so that's what I want to do. So, and the way I want actually to do it, so now like the theorem that I want to prove is that, and this is like Nash's theorem. Okay, so let me state it in the following way. So assume omega is compact. And in fact, assume omega now. If I'm assuming that omega is compact, maybe I can even assume that omega is equal to a ball, just for the sake of simplicity. So let me assume that this one is like, the closed ball inside Rm. Okay, then there exists U in C1 of this ball, and taking values in Rm plus 2, such that U is an isometric embedding, is an isometric immersion. Sorry, let me also not care about being an embedding. Okay, so you see immediately that once you have actually this identity over here, so once you actually solve this equation, automatically the derivative of U must have full rank, which means it must be an immersion. U must be an immersion. So being an embedding is somewhat more delicate because it requires that U is injective as well. Okay, but we are not going to care about that. Okay, so and how I want to do it, so let me first start with a model situation, which is kind of silly. Well, actually, even before getting to the model situation, let me just say that maybe just from the very start. So let me just say that, in fact, I want to set up an iteration mechanism So I want to set up an iteration mechanism which, starting from some approximate solution, produces actually an exact solution. Okay, so therefore, like, the idea is to start with a map, say U0, and then construct a map U1 and so on. And along the iteration, I'm just assuming that all of these maps actually they're as smooth as possible, so they're C infinity. And I just want to show that there is a mechanism which inductively produces from an approximate solution UK. So let's say this one is an approximate solution with a certain level of precision. And what this means, of course, is that I'm actually looking at the target metric G, and I am subtracting what is actually the pullback of the Euclidean metric through UK. Okay, so this is equal to 0 if I am an isometric embedding, but what I'm actually assuming is that I'm not, so this one will be sufficiently small. Right? And I want to produce another solution, which is actually another approximate solution, which is much closer to a solution. So approximate solution for which, in fact, this difference is even much smaller. And of course, the idea is that along the process, I'm actually going to show you that this is possible inductively. So in other words, UK plus 1 will just depend on UK, and it's not going to care about what happened like in the previous steps of the iteration. But we also want to show that this is possible by not only making the, like say, what is called the metric error, which would be this quantity over here. So this would be what people call the metric error. I not only want to make the metric error much smaller, but I also want to show you that it is possible to do this without increasing the, or by estimating the difference of the C1 norm of UK plus 1 minus UK. Oops. Okay, and of course, the objective of this scheme is just to show you that if that there is a way of doing this so that the C1 norm of the difference between two iterates is actually a convergent series. So that in fact UK is a Cauchy sequence in C1, and therefore it's converging to some final map U, which of course, because you're making the metric error smaller and smaller along the iteration, so you make it actually converge to 0, will in fact be an isometric inversion. Okay, so that's what we want to do. Okay, and I'm actually going to like assume something which at the moment is kind of God-given, but you will see what is the reason for assuming this in the iteration mechanism. And this is where some sort of convexity condition is actually hidden. And it's also one of the reasons why these methods are called convex integration. So there's some convexity constraint actually, which plays a major role in the feasibility of this idea. And what I'm going actually to assume is that this metric error is always a positive definite matrix. So I'm just going to assume this. Okay. So this assumption is crucial. We will see in a second, but let me also mention that since we are on a compact set, and we can always like scale our function UK by multiplying by a small factor, once I'm actually sufficiently close to my metric, say I'm like, for instance, delta close to my metric, so the metric error is smaller than delta. If I multiply my map UK by something like 1 minus epsilon, and I like choose this epsilon appropriately compared to delta, I can actually ensure that this condition over here is satisfied, simply because I make actually my derivative just a tad smaller. So all I'm saying is that once you know that this thing over here is small, right? If I actually multiply, so this one here is uniformly small. If I multiply this one by 1 minus epsilon squared, and epsilon is positive and sufficiently small, I will actually be able to enforce that this quantity over here, okay, it has the wrong sign, sorry. So let me put actually a plus over here and a minus. So once actually without the 1 minus epsilon squared, I know that the difference is small. By multiply by 1 minus epsilon squared, I can actually make this strictly positive. And okay, so this discussion is also to say that even if you don't see at the moment what is the reason for assuming this condition, for sure, what I can actually tell you is that if I'm able to close my scheme, I can actually assume this condition without loss of generality. Okay, so let me just play the following game then. So a toy situation is the situation of a one-dimensional. So in a one-dimensional situation, of course, the kind of problem of finding isometric embeddings is trivial because you can always reparameterize in such a way that your metric, which is a scalar, is identically equal to 1. I can always like, you know, change my parameter space in such a way that my metric takes a very simple normalized form. So, and all I have to do in that case, I just have to take my interval, say 0t, and I want to like immerse this inside R3. So I want to actually find a curve which is parameterized over this interval. And if I want to accommodate the fact that the metric has to be equal to 1, the only thing I have to do is I have to actually find a curve of length exactly equal to the size of the interval that I'm given. And I just want to find a parameterization of this curve, which which is an arc length parameterization. So it's a kind of very silly problem, but nonetheless, I just want to experiment on what happens if I'm trying to upgrade a map UK, say from the interval I into R3, which has the property that, say, 1 minus modulus of UK dot squared is positive, and I want to kind of perturb it to a new map UK plus 1, which is going to have 1 minus modulus of u dot k plus 1 squared, much smaller. Okay, so here is the picture. I have my curve. I have my curve over here. And what I want to like to do is actually to like increase the length of this curve by staying like sufficiently close to it. And of course, what you imagine you can do is like, you know, you can just travel around a little bit more. So you can do something like this. Okay, so let me codify this. So let me try now my ansatz. Okay, so let me say that, you know, delta k. So this is going to be a function. So let me actually say that you have this function a of t, and let me define this function a of t in such a way that the square of this function is equal to 1 minus modulus of u dot k squared. And in first approximation, what I want to do is I actually want to like, you know, increase uk dot to u dot k plus 1 in such a way that I actually get this a much smaller. So let me just denote this by ak squared, by ak. Okay, and what I can do is the following. So I can just try to travel around by making spirals. So these are what are called Nash spirals. And let me take just a very precise ansatz over here. So let me take the ansatz that I am actually like oscillating very fast. So let me just put over here, say, the normal to my map UK. So this one is like, say, the normal. So the unit normal, which of course you can just find in formulas by taking u dot k divided by okay. So let me not attempt to do this actually. So this depends on the curvature, so maybe better not do this. So this is just a unit normal field. Okay, and let me put over here cosinus of lambda t, and let me put in front some amplitude. Let me call it A of t. Okay, and then let me put over here a second a vector field B of t, which is suggestive of taking the binormal. So what I actually want is that both n and b are unit normal, and I also want that n is orthogonal to b. So, and that is the reason why I'm actually taking codimension 2 in this construction. Okay, and now I can actually explicitly compute u dot k plus 1, and you will see that something interesting happens. So I have u dot kt, and then I have a principal part, which is when I actually hit, when the derivative actually hits the cosines and sines. And when that happens, I'm going to have this main part of the perturbation. Okay, and then of course it might happen that the derivative like falls on the coefficient a or on the vector fields n and b, but what is happening is that then I'm not actually touching this big denominator lambda, right? So I'm only touching it if I'm actually differentiating the fast oscillating functions, cosines and sines. Okay, and so here I actually get a big O of 1 over lambda. Okay, so this is interesting because now at this point, if I'm actually going to compute the modulus of u dot k plus 1 squared, I can explicitly compute it. And what is going to happen is that modulus of uk plus 1 squared is just going to be, and now notice what happens over here, right? I mean, since I actually have chosen that this vector field over here is normal to the curves, so in particular, it's normal to this vector here. And since I've chosen B in such a way that it's not only normal to u dot k, but it's also normal to n. So I'm actually summing over here 3 vectors which are all normal to each other. And so the modulus of this part is actually going to be the sum of the respective moduli. And you see that there's like a sine squared popping over here, a cosine squared popping over here. So the sum of sine squared plus cos squared is actually equal to 1. B and n are unit. So the length of this part is exactly a squared. Okay, and now this is the computation. Okay, and then I have like some errors because of course I need to take into account that there is also this third part of the derivative, but anytime that I'm actually involving this third part, I get a rather small number. Okay, so and let me just summarize this with this big O of 1 over lambda. Okay, of course, now once you have this, remember that what you wanted to achieve was something like of the following kind. So you wanted to achieve a new element in your iterate, which is still positive, but with the property that this is actually much smaller than what you had before. Okay, well, whatever you had before, of course, now you just have the freedom of choosing a squared. So choose A so that, say, this thing over here, 1 minus modulus of uk plus 1 squared is something like any delta k that you want to choose. I mean, this delta k could be as small as you want. And now choose the perturbation big O of 1 over lambda in such a way that this one is, say, less or equal than much smaller than delta k. I mean, for instance, it could be like less or equal than say delta k divided by 2. Okay. And so if you make this choice, at the same time, you're assuring that this thing is positive. And it's less than like 2 delta k. Okay, so you got it much smaller. And now, of course, you just need to choose the delta k going to 0 so that you become a better and better approximate solution of your isometric embedding problem. Okay, on the other hand, go back to the computation of the derivative and look at what is the difference between u dot k plus 1 and u dot k. So the difference is just this factor a, essentially. Right, so this is really what is giving you the difference. Okay, so it's this factor a plus something which is actually small, right? So it's this big O of 1 over lambda. Okay, so roughly, you also know that the C1 norm of UK plus 1 minus UK, right? So in C1, this is roughly a constant times the C0 norm of this factor A that you wanted to add, okay? But how can you actually understand how big this is? Well, this factor A is essentially as big as as 1 minus u dot k squared, right? So certainly it's not going to exceed this quantity over here, right? Okay, so maybe just for being consistent in this, let me actually say that this one is like, I don't know, delta k plus 1, right? So that you have here k plus 1 and k plus 1, so they match. Okay, so now it's easy to see that somehow this choice of A, because you don't want u dot k squared plus a squared to actually exceed 1. So you certainly have the inequality that 1, okay. You certainly have the inequality that 1 minus modulus of uk squared is bigger or equal than ak squared. Okay, and now if each time you're actually having that this difference is no larger than 2 delta k plus 1, so here of course you could say that, well, inductively I can keep that this difference is actually at most like 2 delta k. Okay, and so here you just find that this one, it goes like a constant times square root of delta k. Okay, and now you are in business because you have an iteration mechanism to actually improve your solution to be your approximate solution to be a much better approximate solution, and you have a way to actually keep under control the C1 norms, right? So now you just need to choose that the delta k go to 0 in such a way that the sum of this series is bounded. Okay, and this actually guarantees C1 convergence. So you have at the same time C1 convergence, and the limit is a solution. Okay, so maybe this is actually a good place to make a break, I guess. I mean, you don't want to hear me going on for like, 2 consecutive hours. This is probably too much. So let me propose, if Marshall agrees with me, let me propose that we make a say a few minutes break. So okay, so now let me just tell you that now I have like the more general problem, right? So and let me try. So now let me say that I have this G, and I have this G minus UK sharp E, which okay, so this one is bigger than 0 and small. Okay, and now let me just make the following assumption. So, so first of all, what this is really, so this is like G minus DUK transpose times DUK. Okay, and let me try to play the following game. So let me just try to write UK plus 1 So let me just plug in an ansatz, very similar to what we did before. So let me just write it as UK. And then let me think that I have many directions at my disposal in which I actually want to oscillate. Okay, so these directions, I'm just going to call them VK. So VK, well, let me call them actually VJ. So VJ are just directions in my original sample. Okay, so remember that I'm just looking at, like, this omega, which is a ball. And so here I have many directions, like, V1, the direction V2, and then direction V3. There are many more actually that even the dimension of the space. Okay, and for each of these directions, let me assume that I have a vector fields BI and NI, which are all orthogonal to each other. So here I'm then going to have like NI of X, and here I'm just going to put cosinus of lambda. And now here I put VI dot X, and I have then VI of X, and then I have sinus of lambda VI dot X. Okay, so let me just plug in this ansatz. And let me assume, as I said, that, Ni is orthogonal to Bi, Ni is orthogonal to Nj, Bi is orthogonal to Bj, and all are units. They are all units. Oh, and they are all orthogonal to the tangent, to the tangent space, to the immersion of my omega UK. Okay, so which means that if I take duk of, say, Rm, right, understood as a linear map at any point x, so this is a space, and Bi and Ni are both orthogonal to this guy. Okay, so now I'm going to make exactly the same computation, and when I make the same computation, I get duk plus 1 is equal to duk. Okay, and then I have the sum for I equal 1 to n, and the first part, I just get the following thing. So I get minus n.
Camillo, we lost you. Camillo, we lost you.
You lost us?
No, you're back.
Oh, I'm back. Okay, can you hear me?
Yes.
Okay, wonderful. Sorry. So where did you? So you lose me when I was doing the computation, I guess, right? So no harm done.
Yeah.
So I'm just making the computation, and of course, this is what happens when I'm differentiating the cosines and sines, right? So in terms of matrices, this is like, I get the differentiation of this function vi dot x. So it just gives me actually vi, because I'm assuming that these vi's are frozen. Okay, and then I get a big O of 1 over lambda. Okay, so now I have actually the very same structure. Oh, and I'm forgetting. So here I want to actually also have the liberties of fixing coefficients AI, which I'm going to choose later. Okay, so these coefficients AI, then they're going to be over here. Okay, so if you're looking at what happens now when I'm taking the duk plus 1 transpose times duk, again, because I mean it's just a slightly more complicated linear algebra computation, but because of the orthogonality conditions that I have among all these pieces, right, I don't actually get mixed terms. Okay, I don't get mixed terms, and you can just check the computation yourself. What you're actually going to get is the following. So I'm going to get duk, and the sum of the squares of these terms are actually going to give me ai squared vi tensor vi. Okay, and then there's like, a big O of 1 over lambda. Okay. So now, what do I So I actually know that this one is approximately G, right? So if here I add a G minus, right? So let me actually add a G minus over here too. Okay, and then let me add the minus. Okay, now you see that if I want, like, you know, if I want this one to be very close to 0, so if I want this one very close to 0, what I can do is I can just solve for this AI squared. So I can solve actually for this linear problem that I have to choose the coefficients AI squared in such a way that this sum is going to give me this part over here, right? So in other words, what I'm just saying is that if I choose the green part in such a way that it's equal to the purple part, right, then that part will be equal to 0, and then I have this perturbation, which is 1 over lambda, which I can actually make very, very, very small simply by choosing lambda very small. So notice that this one is totally independent of lambda. Okay, so let's say that I want to do that. If I to do that, of course, I can do it instead of, you know, making it exactly equal to 0. As I was doing before, I can actually make it equal to something positive but small, and then I can choose lambda very large in such a way that when I actually add the errors, this positive but small remains positive and small. Okay, so therefore, I'm not going to care too much about this error over here. So I just ignore it. Okay, I ignore it and I want to solve this. So what do I want to do actually? So here there's like this one here. So what do I want to do? Well, I actually have just a linear algebra problem. So I have here a positive definite matrix, and I want to write it as a sum of positive semi-definite rank 1 matrices. Okay, and I obviously can do that. I mean, for instance, if you give me just a single matrix, I diagonalize it and I put actually things on the diagonal. But you can imagine it's a simple linear algebra question just to say that, for instance, you can do it not only for the single matrix, but you can do it if you have a sufficiently large basis, or if you have a sufficiently large collection of these VI tensor VI, you can actually do it in a neighborhood of any positive semi-definite matrix, right? So if you see actually here that what I want to do is to write something essentially as a positive linear combination of some basic choices over here. And if I have, say, these guys that are more than the dimension of the space, then this VI tensor VI typically will actually span a simplex. The convex combination of these guys will span a simplex which has a non-empty interior. Okay, so this is actually easy. So this is an easy linear algebra problem. And you can even guess locally how you want to do it. So you can guess that locally you can do it with a number n, which is in fact the dimension of the symmetric matrices. So you should actually be able to do this with something like n times n plus 1 divided by 2 vectors. I actually believe this is m in my notation thus far. Okay. So that actually takes care of the problem. Let me just make the following make the following remark too. So this is actually very nice. Oh, sorry. So remark. This is actually very nice and it's easy to implement when your domain is a ball. But what is happening if you actually have a Riemannian manifold sigma, which is truly with non-trivial topology? So if sigma has non-trivial topology, you can actually do this locally on a chart, right? So on a chart which is a ball. So you imagine you have something which is like, I don't know, something like this, which is complicated, right? And then you can actually do it locally on a chart like this, right? And I mean, locally you have a chart, you make a change of coordinates, and then you find your directions, say V1, V2, V again, and you make your decomposition locally, okay? But then, of course, you have just accommodated your metric on a chart, but you've not actually accommodated your metric on the other charts. So what you can do, though, you can just split your objective metric error, so the one that you want to correct. So you remember that what you want to do is you want to correct actually for this guy. Okay, so if you call this one H, right, and what you actually want to solve is for the sum of the green terms equal to this purple term, which is equal to H. So what you can break H, right, into a sum of phi I times H for some partition of unity.
We have lost you again.
Can you hear me?
Yes.
Okay, sorry. The connection sometimes, I don't know why I'm having problems. Usually I don't, but it's not my fault. I'm actually in the office, so I can't get it.
I think it's your audio, Camillo.
Sorry?
It's just your audio for some reason.
A very short time. It's okay.
I think it's the connection. The connection sometimes, like, you know, drops for a few seconds, and the audio is, and then you're losing the audio.
Actually, we're not losing you. When you bend writing, you don't speak to the microphone. That's when we lose you. Not lose you completely, become very weak voice. That's all. So just speak straight. That's all. Continue. That's fine.
Wait a second. So, but can I do something about this? I can switch. I have a computer. I'm logged in.
No, you're doing fine. I think, Laszlo, you're doing fine.
Okay. Okay. Very well.
Oh,
So
I meant Camillo. Sorry.
no problem. Okay, so you can actually make a partition of unity over here, and once you make a partition of unity, you see that you have to solve your problem in each chart, right? So instead of solving for the sum of the AI squared vi tensor vi equal to h, you want to solve for this one equal to h times phi I squared, right? But of course, at this point, what it really means, that is why I actually inserted the squared. What it really means is that you simply multiply your AI, which you found in your chart, by the function phi I, which is kind of, you know, the square root of the partition of unity, if you want. Okay. So and I want you to remember this trick, because it's going to be this kind of localization procedure is important. Because it's a kind of you know, toolbox. It's a tool in your toolbox that is going to play an important role later on. Let me just also remark, you can't do this localization procedure at the level of the directions in which you oscillate. Okay, so careful, you can't choose. So you cannot choose the VIs depending on X, which is the other choice that you might actually be, you know, tempted to do when you're passing from one chart to the other. And the reason why you can't do that is because when you go back to your ansatz, let me write it for you over here. So you remember your ansatz has the following, writing. So you remember you have the lambda, and then here you have the VI. Now, if you make the VI of X depending on the VI depending on X, you now notice that when you actually differentiate this, remember what I really care about is when the differential hits the lambda, which cancels the lambda at the denominator. So then I get something like this. Of course, I get the derivative hitting this X. So this one is the portion I'm happy. But then I also get the derivative like hitting the VI. Okay, and then that I'm less happy with. Okay, because now I can't anymore like think that this one is really the principal term. Right, because this other term is at least as big as what I was looking for. And of course, you see that I have lost the big advantage that I had before. The big advantage that I had before is that when I was actually trying to solve for this green part equal to the purple part in here, the big advantage is that I just got a problem which is purely algebraic because no derivatives of the AIs are appearing. If I try to do something similar with such an ansatz, well, now here, I actually have the derivatives of the VI appearing, right? Okay, so now the situation gets more complicated. Okay, so I have to actually choose the VIs accordingly in such a way that, you know, the algebra is going to work with the AI. Okay, so let me just get to the following basic deconstruction of this scheme of Nash. So now it looks very, very specific. And so if you actually try to understand whether something similar can be run on another system of PDEs, it's not so clear where you would actually like to start. Okay. So let me start with the following first. So the like say first step that Laszlo was presenting in his lecture here at the institute. So this is what he called freezing the coefficients. Let me actually call it freezing the previous map. Okay, so as you might have noticed, like at each step of the iteration, it actually happens that I am adding a very high oscillating ansatz. Okay, and the previous iterate is like varying in a much slower way, right? I mean, in particular, you notice that anytime that I'm writing big O of 1 over lambda, for instance, in this blue term over here, I'm actually sweeping under the rug a dependence on the previous iterate, right? So because, for instance, in this big O of 1 over lambda, there are terms in which I actually differentiate the normal vector fields Ni and Bi. And if I want to choose normal vector fields Ni and Bi, of course, these vector fields will depend on the derivative of the previous iterate, which gives me like, you know, the tangent space to which I want to be orthogonal. And so when I'm differentiating Ni and Bi, actually what I'm seeing are like second derivatives of the function UK, okay? And then I'm taking this lambda very big, which means that at all effects, my perturbation is actually changing at a scale which is much, much smaller than the scale at which my previous function has the first derivatives which are changing, right? So the second derivatives of the previous function have a certain size, and this big lambda has to beat them. I mean, has to be much, much bigger. Okay, so this means that for our purposes, we can consider that the previous function, so the previous iterate, is actually at a constant derivative. So the UK is a constant. Okay, so if the UK is a constant, then like let me just also like just say that you know, if instead of looking at it, because in later it will be actually useful. So let me just declare that in fact what I want to do is I want to add so a certain function to the UK, and the certain function that I want to add is actually a function which is curl free, right? So because it has to be the derivative of another method. Okay, so in other words, let me just say, so here I want to add the perturbation. Let me call it WK plus 1. So this is like going to be the perturbation that I want to add. Okay, and instead of focusing on the fact that I'm adding a perturbation which has to be an exact derivative, okay, so let me actually focus on the fact that I want to add the perturbation of the following type. So I want to add a big function WK plus 1, which is depending on slow variables and fast variables. So it's going to have like, you know, a shape of the following type. Okay. So this is actually WK plus 1 that I want to add. Okay, and the reason why I want to do this is because in a sense it mimics this construction over here, right? So this one is the fast variable, and this one is the slow variables. And I kind of want to decouple them. So let's say I want to actually call this thing over here like Y. I want to think that I have another variable and I'm putting like Y equal lambda X. Okay, so let me do that. So therefore, I'm just looking for like, you know, WK plus 1 of X, Y. But actually, let me highlight that, in fact, what I really want here is I don't want actually X, but I want to replace this X with something else. So in fact, I want a function okay, which is depending on the metric error. So this is what we called H. Okay, and it's depending also on this derivative. So this is the DUK. So this I will actually call A. Okay, and then there will be like the fast variable over here, and that is Y. And so the dependence on the slow variable will actually be because in the final definition, my perturbation will take the following shape. So it will be big W of K plus 1, and then I actually want to add H of X, and then I want to add A of X. Okay, and then I want to add over here lambda X. Okay, so that's what I want to do. Okay, and sort of this, in a sense, gives me a way to focus on the important part of the perturbation. So now what I'm left with is, you know, I have some objective H. So you remember this was like the deficit, right? So this was like G minus D UK transpose times the UK, which actually now for me is like G minus A transpose times A. Okay, and I'm freezing the coefficients, so I'm actually thinking that G is a constant, right? So that this H is also a constant, and the only thing I know about this H is that H is simply positive. Okay. Very well. So now, if I'm actually doing that, let me just think at what I want to do. So I want to add this perturbation over here in such a way that now I'm canceling that H, right? So that I get actually to G. Okay. So the thing that I actually want to do is I want to find a solution of H minus, right, dyw times okay, transpose times dyw equal to 0. So, and it only affects somehow what I actually want to achieve. Now, let me just make another, like, you know, change of perspective. This was 1, 11. So now let me actually make another change of perspective. What I actually want to do is I want to find, you know, perfect derivatives which are solving this guy over here. Okay, so let me write it in the following way. So what I actually want to solve is, say, finding for a function z with z transpose times z equal to my function h. So now what I want to do is I actually want z, which is depending on h, which is depending on a. Oh, right. Okay, so h is actually going to, let me just write it in the following way, right? So this is going to be, okay, I don't want actually independent on h. I actually want dependent on g, I guess. No, it's fine actually. So it's not going to depend on h. That's fine by me. So I want a function which is depend on z, h, and y. Okay, and what I want actually is that the curl of z in y is equal to 0. And z transpose times z is actually going to be to this constant function h. Okay, but not only that, of course, what I also want is that, you know, there's the potential for this z, which when I periodize my, because you see this function y, I actually want to be in the periodic torus, right? So I actually want the periodic solution. So I want to find a potential which is also periodic. And in order to do that, not only I have to solve that the curl of z is equal to 0, but I also have to, like, you know, accommodate for the condition that the average of z is equal to 0. Okay, and so in a sense, what I'm actually looking is I'm looking for a specific, a multi-parameter family of PDEs. So you see that the PDE is going to be, you know, this curl of z is equal to 0, this z transpose times z is equal to h. But I'm looking for, like, you know, a finite dimensional family of these solutions, which depends on these functions h and a over here. Okay, and of course I want a smooth dependence on little h and big a. At the same time, I want actually a periodic variable over here, because this is the variable that I will actually make go fast, which I will multiply by lambda. And of course, you might at first object that look, if I only solve for the curl equation in the fast variables, right, I can find a potential, of course, for each h and a for this z, but it's less clear that I am actually going to find a potential for this function, for this z of, say, h of x, a, say, of x and lambda x. So this one is not anymore curl free. So the curl of this, of course, right, is going to have the lambda times the curl y of z, which is actually equal to 0, but there's going to be some more terms which are coming from the curl and the derivatives of H. So there's going to be a dH term in Z, and there's going to be like, a dA term in Z. But you will notice that since I have actually these fast oscillating variables, I will actually be able to correct for the fact that the curl is not equal to 0 by simply adding a little correction. Or in other words, if you want, what I can do is I can simply say, okay, once I know that I have solved for the curl in Y, let me just go and write, ZH of a Y as the gradient of some master function in Y. Okay, and now the ansatz that I actually have to put is, okay, so now what I want to do is I want to actually define my, say, Z prime of X, say lambda X. I actually want to define it to be W of H of X, A of X, and then here I'm going to have lambda X. Okay. And now you will notice immediately that when I actually, well, of course, the curl of this Z prime, okay, so this is going to be like the gradient of this. Of course, now notice immediately that the curl of my Z prime is equal to 0. And you also notice that the difference between my Z prime and my Z, okay, so here I have to put a 1 over lambda. And you notice that the difference between, say, Z and Z prime, right, is going to have this 1 over lambda feature, which is popping in front of things, right? So here I'm going to have something which depends on the H of W, and it's multiplied by the H, and then I have something which depends on the A of W, and is multiplied by A. Okay, and here is where you see somehow the 1 over lambda, which is popping out in Nash. And of course, here you also see why I insist on having that my family depends kind of smoothly on H and A, because when I actually am differentiating this big W function, master function, via H and differentiating this big W function through A, I don't want to get something which is too big over here. So these ones, I want them to be under control. Okay, so this actually kind of is a kind of abstraction which I want to apply now to the Euler equation. But let me come to the question by Steve. So by Steven. So what happens when I actually want to lower the codimension? So when I actually want to lower the codimension, one first thing that you might notice is that I don't need to. So first remark. Okay, I do not need to so first of all, I do not need to add all the corrections A squared VI tensor BI all together. But I can actually add them one step at a time, so that I can only use like, 2 orthogonal directions to do that. So in other words, what it actually really means is that in this scheme, I don't really have to like, solve this thing immediately, but I can actually think that I'm actually solving into subsequent steps in which I first add a perturbation that keeps H, reduces H in a certain direction. Then I can add a second perturbation which reduces H in some other direction and so on. So I can like, before doing this, I can actually decompose H in pieces which I can solve, or in pieces which I can kill. Okay, and then add the perturbation serially. Okay. Now, what happens when I want to pass from codimension 1 from codimension 2 to codimension 1? Well, what happens is that I will not be able to actually oscillate anymore in a direction which is orthogonal to the derivative of u. So I will actually have to like oscillate in a direction which is also like, you know, parallel to u. So this means that when I'm going actually to solve this identity over here, I will not only have z transpose times z equal h, because what I'm really having is something like this. So I'm really having like something like a plus z transpose times a plus z equal g. So instead of having only the quadratic equation, I have something which is more complicated. Okay, which means that instead of having these ansatz in which I have to solve like, you know, a linear expression which is easier, I actually have something which is more complicated, and I have to find the solution of my systems of PDEs which is more complicated. And now first you can ask yourself whether you have a solution. And okay, so instead of having sines and cosines, you actually have to plug something which is more precise in this case. And let me add another comment. It might not be, I mean, it might be that you're actually not exactly able to solve this precisely. So at all effect, maybe what I just want to do in first approximation is solve this one plus a small error. So error, which I can add. So let me just wrap up what we have learned. So what we want to do is when we have a certain system of PDEs, we actually want to cook up an iteration mechanism in which we have a high frequency perturbation of the previous solution. And I have a certain amount of tools at my disposal. So the first of all, one tool is that I can essentially forget about what we call the slow variables, or we can forget about what actually happened at the previous iteration, because what is happening, so what is the perturbation that we want to add is oscillating at a much faster speed. So for all that we're concerned about, we can actually treat the previous approximate solution as something which is constant at the scale at which we are looking. Okay, so at that point, we actually have the PDE in the slow and the fast variable, but we can completely ignore the PDE in the slow variable. What really counts is actually the PDE in the fast variable. Okay, and then if we are looking for an ansatz which is like getting us a much better solution or a much better approximate solution compared to the previous one, what we actually end up with is looking for a multi-parameter family of solution to a certain PDE problem which satisfies certain constraints. Okay, so let me just go now directly to Euler and show you what I want to do over there. Okay, so here it is. So now I'm actually assuming that I have actually a sequence of solutions of the Euler equations, and these are just continuous. Okay, so now these are not exactly solutions of the Euler equations. I have an error. And let me quantify this error as something that I write as the divergence of something. So now here is the first time that I have to invent something like, you know, before in the problem that I had the metric which I wanted to achieve, and what I'm doing is I'm achieving it as a sequence through a sequence of approximate solution, which gets the metric difference between the the metric that I want to achieve and the pullback smaller and smaller. And now what I want to do is I want to introduce a similar error in being a solution of the Euler equation. And what I'm actually going to do is I'm introducing this error in that divergence form. Okay. And then I have my divergence of UK equal to 0 over here. Okay, very well. So now what do I want to achieve? Well, I want to perturb my solution UK plus 1 as a function UK of x, and then something which is very fast oscillatory. Okay, so it's something which I'm actually going to write as big W of x, lambda x. And what do I want actually on this big W of x lambda x? Well, okay, so first of all, as you might recall, we have this PDE to actually satisfy. And what we did, like in our previous in our previous considerations, is we kind of forgot the part of the PDE which affects this variable over here. I mean, to all effect, what we really want is that this is divergence free, but instead of looking at this to be divergence free, we are going to look for something which is divergence free only on this slot. Okay, so I'm just going to actually impose this first condition, which is the divergence y of W. Oh, and maybe this I should actually also take care of. These are solutions of the Euler equation, so they also depend on time. So let me do something like this. Okay, so therefore, let me just think about these as the fast and slow variables. Okay, let me do it this way, actually. And so this is the first condition that I want to satisfy. Okay, so this is condition 1. Okay, now remember that actually I want to consider this big function W in the slow variable as really a function which is depending on, and of course here I will have to add a correction to make it divergence free. Okay, but this is a correction to make it divergence free. This is going to be small. Okay, but I really want to think it's this function W as, in fact, depending on this function R and the previous solution. So what I'm really looking for is a master function W which depends, in fact, on big R, and let me call it V for the slot which I actually want to put in UK. Okay, and then I will substitute U of xt, UK of xt over here, and RK of xt over there. Okay, and now let me see what I really want to achieve, right? So RK will be computed later on. RK plus 1 will be computed later on as our error from being a solution. So let us actually focus on the main part of the equation. So this is going to be something like this. So dt UK, and then there's going to be like slow derivatives. So so there's going to be like lambda times d tau of W, and this is like in RK UK of x and t, and then I'm going to have lambda x lambda tau. So first of all, I'm only differentiating in the fast direction. So there's going to be, if I now write this one here as uk.grad uk. So there's going to be like, an advective derivative, which is going to hit my fast variable. Okay, and then there's going to be again a lambda term in which I have the divergence psi of big W, and this one is also computed in RK UK lambda X lambda tau tensor. Okay, and of course I have a similar ansatz also for what I want to add to the pressure. So let me just add it over here. pk plus 1 of x and t. So this is going to be pk of x and t plus, again, a big function p of x and t, and there's going to be lambda x, lambda t. Okay, and then let me just simply say, okay, so there are other terms, and let me not, for the moment, let me actually not care about these other terms. Okay, then we are actually going to look at what they are. Okay, and all of this actually has to be equal, and then here I'm going actually to just say that this one is going to be the divergence of my next tensor RK plus 1. Okay, so one first thing that I can actually observe, so so it seems I am in a different situation compared to what I was in Nash, because I would just put the ansatz, then compute, and then I get the metric error. Okay, and this is what I'm given. So this is something that I compute. Now it seems actually different here because I have to compute an RK plus 1, which actually satisfies the divergence of this equal to the left-hand side. Okay, but in fact, it is possible, and this is not difficult, so it is possible to invert the divergence operator. So more precisely, it is possible to find something which I will call divergence to the -1. Let me call it divergence to the -1. Okay, with the property that so divergence to the -1 of whatever vector field I'm actually feeding, which I can call, I don't know, little z, is exactly equal to z, at least if the average of z is equal to 0 on the torus. Okay, so in analogy with solving like divergence of a vector field equal to a function, so if I want to solve the divergence of a vector field equal to a function, what I do is I actually solve for the Laplace equation. So if I want to solve, for instance, divergence of say an unknown vector field x equal to some function f, what I can actually do is I can plug for x like gradient of Laplacian to the -1 of f. But to be able to invert the Laplacian, of course, I need a condition, and the condition that I need on the torus is that the average of f is equal to 0. Okay, and there is some sort of canonical choice even for this situation, in which here I actually want this RK plus 1 to be a symmetric tensor. Okay, so I can solve for the RK plus 1 I'm sorry that I'm going a little bit extra time, but I promise I'm actually wrapping up this in a few moments. So I can solve divergence to the -1 of whatever I have over here. So this is this big expression. And certainly one thing that I want to do is I want to actually completely kill these terms which actually have a lambda in front. Okay. And if I want to do that, of course, I need to solve now a PDE in, as you see, tau and psi, right? So if I look at what I want to do is I actually want to solve a PDE, which is the tau of my function big W plus v dot grad psi of my function big W plus divergent y, divergent psi, sorry, of my function W tensor W plus gradient psi of P is equal to 0. Okay, so I've now found like, you know, my multi-parameter family of solutions of the Euler equations, or of some sort of perturbed Euler equations, which depend on the parameter V over here, right? So if you actually combine this condition with this one, what we have is our kind of PDEs, which we actually want to solve with this multi-parameter family of solutions. Okay, so of course, this just tells you that I've actually killed the terms with a lambda, but let us just go only a little bit further and show you one thing. The lambda is equal to 0. What is happening to the other terms is that I'm having dt of UK, of course. I'm having actually the previous solution, which is divergence of UK tensor UK. Okay, and now let me do something interesting over here. So you see, here I wrote that I have divergence psi of W tensor W, right? So I can actually subtract from here the averaging psi. I can subtract from here the averaging psi of my function W tensor W, because this function now does not depend on psi anymore, and so I'm actually not seeing it in this divergence condition. Okay. But it's still a function which depends on x and t. Okay, and so let me keep it over here. Okay, and then I have other terms. And now what my RK plus 1 is going to be is a divergence inverse of these objects over here. Okay, and of course I have also gradient pk. And now actually I'm not going to show you, but what is going to happen, well, we will make some more precise computations, is that all these other terms, when I'm applying this divergence to the -1, I'm actually getting a 1 over lambda. So the divergence to the -1 of all these other terms gives me a 1 over lambda. Now, what is actually happening for these things? So for these things over here, I can use the previous iterate to just say that that one is actually the divergence. So here I'm finishing up by having the divergence to the -1. And then here I'm having the divergence of the previous iterate, which is RK, And now what I'm going to have over here is W tensor W averaged in psi. Okay, and lambda, but this one doesn't, and this one I really want to be able to zero, and this is where I will actually impose that this condition is equal. Okay, so now this gives me this extra condition, which tells me that the averaging psi in the variable psi of the W tensor W has to be equal to minus R. Okay. Now there's a last actually condition which I should have added. If you remember, when we were actually satisfying the curl-free constraints, we passed to a potential. And to have a potential which is periodic, we wanted actually that the average of our solution was equal to 0. So we want to do something like that here as well, because otherwise, when we're saying that in this computation over here, when we're saying that all we have to do here is to add a correction. So for this condition to be true, I actually want that the average in psi of my function W is also equal to 0. Okay, and so this is like, you know, an extra condition that I want to add. Okay, and the only thing I actually wanted to say is that even though this problem looks very different from what Nash was doing, there is a way of interpreting Nash which you can actually transpose over here. And the first thing that you can do is, if that you can infer from this method, is the following. So assume that I want to run an iteration like the one of Nash. What are the conditions that my highly oscillatory perturbation has to satisfy? And the conditions are these four that I've actually written for you. So you want a multi-parameter family of solutions W and P, which are depending on these unknowns R and V smoothly. And you want some algebraic conditions that they satisfy, which relates the average of your functions to the unknowns R and V. In this case, actually, the V does not appear over here. It appears only in the PDE, but it might as well actually appear over here. And so this is just like a coincidence of the problem that you're trying to analyze. Sorry for going extra time.